Hey, folks. Oops. Let me see what's happening here. Okay, that is muted. Let me see. Let me stop sharing for a minute. That is muted. So why is it? Why am I hearing an echo? Let me mute this. Okay. All right. So let's see. Chessmore is here. Miller is here. And Peterson is here. What's your last name again? Simpson. Simpson is here. And Wilker will be here shortly. All right, so let me share my screen. And let me just say that as you have probably noticed in a particular email I had exchanged with one of your fellow students, I've decided to put off the test until Wednesday. So, and the reason for that is because I was a bit behind in terms of posting the answer keys for the second assignment. So it's there now. And also for future reference, in terms of videos, I've been having some issues posting the videos online, even though I'm recording the videos right now. But I've also recorded some videos in the past, which are available under the module section. So if you miss a class, then you can go there to basically cover on your own what we would have covered in lecture. All right. So I just thought I should let you know about that. So what I'm going to do now is go straight into the next topic, which deals with the comparisons between strong and weak electrolytes. And this is something you would have or should have met before in General Chemistry 1, but we're going to get into it in a more quantitative sense in this section, right? So we all know what a strong electrolyte is. It is basically a compound which, when added to water, completely breaks up to form ions. all right? So for example, if you take sodium chloride, add it to water and it dissolves, then all the sodium chloride that has been added to water will be converted to free ions that are floating around in an aqueous solution. So if you could actually see the particles, all you'll be seeing is the sodium and chloride ions floating around. You will not see any intact sodium chloride units present in the aqueous solution. A weak electrolyte, on the other hand, does not undergo complete dissociation. And a good example of this is acetic acid. Acetic acid, when added to water, the result would be only a small fraction of the molecules that goes into solution will be converted to ions, all right? And you should have learned that one of the things that we can do to actually observe the differences between weak and strong electrolytes is the fact that you can design an experiment to see whether or not it conducts electricity, right? So strong electrolytes will conduct electricity very well, while weak electrolytes will conduct electricity, but not as strongly as in the case of a strong electrolyte. So that's one essential difference between those two. Now, the term strong and weak not only applies to electrolytes per se, but also specifically can be applied to acids and bases, right? So we have strong acids and weak acids, right? Strong acids are also strong electrolytes for the same reason why sodium chloride is a strong electrolyte, right? So a good example of a strong acid is hydrochloric acid. When you add HCl to water, you're going to end up with a complete dissociation. In other words, in any solution of hydrochloric acid, you will not see any intact HCl molecules present, right? All of it will be converted into the hydronium and the chloride ions as indicated, right? And I remember asking you guys if you remember the 6 strong acids, and most of you said, no, you don't remember. So again, I'm going to ask you, what are the 6 strong acids that you should know? The 6 strong acids, anybody?
HCl, H2O, SO4,
Mm-hmm.
HNO3,
Mm-hmm.
HBr,
Mm-hmm.
HI, HCl.
Exactly, right? So those acids, all those acids that he just mentioned, are strong acids and will undergo complete dissociation when you add them to water, right? So HCl is one example. Another example is nitric acid. Another example here is perchloric acid. And the 4th example here is sulfuric acid. And the 2 other examples would be hydrobromic and hydroiodic acid, right? And what these all have in common is complete dissociation when added to water. And we represent that complete dissociation by using the one directional arrow that is shown here, as opposed to in the case of weak electrolytes or weak acids, which we're going to talk about shortly, you have the double arrows shown here, all right? So basically what this indicates is that eventually, if the mixture remains in an aqueous solution long enough, what will happen is an equilibrium system being set up, right? Where you have the rate of the forward reaction going in that direction equal to the rate of the reverse reaction. And therefore, all that we discussed in terms of equilibrium in the previous chapter will apply to systems such as systems involving weak electrolytes. So these are strong electrolytes. And then we have weak electrolytes, weak acids, I should say, such as hydrochloric acid. We met one before, acetic acid. In the case of hydrochloric acid, it undergoes partial dissociation, as you can see here. So as you can see here, we have a double arrow indicating that we're going in both directions, all right? Eventually, equilibrium will be established. Here's another example. In the case of nitrous acid, it will also undergo incomplete or partial dissociation. A third example would be the hydrogen sulfate ion, which is formed from the strong dissociation of sulfuric acid. So I think I mentioned that last time, that sulfuric acid that has 2 hydrogens that you can lose when it adds to water. But the first dissociation is strong, but the second dissociation, which is represented here, is weak, all right? And here's another example, and you might be surprised at this. Even water itself can behave as a weak acid. In fact, it behaves as both an acid and a base because it releases hydronium and OH minus ions. So water can be said, based on this equation, to be amphoteric. Let me write that term down. Amphoteric basically means that a substance is acting as both an acid and a base. So in the case of water, it is said to be amphoteric. Terrific. All right, okay. So those are the weak acids, and then we can apply the same terminology to bases. We can have strong bases and weak bases. So strong bases are strong electrolytes. They undergo complete dissociation, such as sodium hydroxide, which will undergo complete dissociation to form sodium and hydroxide ions. And again, you see the arrow pointing in one direction. Here's another example, potassium hydroxide, which will undergo complete dissociation to form potassium and hydroxide ions. And then we have barium hydroxide, which will also behave similarly, undergoing complete dissociation to form barium and hydroxide ions. So that's basically how bases are. And then we have weak bases, which are weak electrolytes. And as you can see in the example shown here, the fluoride ion is acting as a weak base because it produces hydroxide ions, but you have this back and forth again taking place where the system will eventually achieve equilibrium, right? So we represent that with the arrows going in both directions, all right? Here's another example, the nitrite ion behaves similarly. So that's basically how bases and acids behave in terms of their strength. Then we have this term, conjugate acid-base pairs, all right? So basically, what you'll find is that some general things we can observe in terms of the strength of conjugate bases that are formed when an acid loses protons. First thing that is mentioned here is that the conjugate base of a strong acid has no measurable strength. So basically what that means is that if the acid is very, very strong, you know, like hydrochloric, nitric, and so on, that means that the conjugate base formed from those acids will be very, very, very weak. In fact, so weak that it has no appreciable effect on the environment in terms of the aqueous environment. Another point being made here is that the hydronium ion is the strongest acid that can exist in an aqueous solution, and the hydroxide ion is the strongest base that can exist in an aqueous solution, right? So basically, when you add an acid that is strong to water, then what will happen is that that acid will simply dissociate to form the hydronium ion, right? So if the acid is stronger than water, it will form hydronium ions. In chemistry, we call that the leveling effect, all right, where basically the acidity of the acid is level to that of the hydronium ion when it adds to water. And then the same thing happens in the case of bases. If you add a strong base to water, then basically the base will dissociate so that the strongest base that can exist in an aqueous solution will be the hydroxide ion. So that's another example of the leveling effect. So this is just basically showing you the relationship between the strength of an acid and the strength of the conjugate base formed from the acid, right? And basically what you see here, we can actually show this quantitatively, that as the acid strength increases, the base strength decreases going in this direction, or vice versa, right? So there's a kind of inverse, in fact, not kind of, there is an inverse relationship between the strength of an acid and the strength of a base. So if you take the strongest acid here, perchloric acid, right? Very strong acid, the perchlorate ion will be a very, very, very weak base, all right? And then as you go down here, this acid here is relatively weak. The amide ion, which is the conjugate base of ammonia, will be a very, very strong base, all right? So this is a pictorial representation actually demonstrating the difference between a strong acid and a weak acid. And we talked about this earlier, but this is just a pictorial representation. If you start off with a strong acid like hydrochloric acid and you add it to water and then it undergoes ionization, it undergoes complete ionization. So therefore, the only things that are left after you add the acid to water will be hydrogen ions or hydronium ions and the chloride ions and water molecules, obviously, right? But basically, you won't have any HCl present, all right? You won't have any intact HCl molecules present under those circumstances. Realize that this was in the way. Okay, so in the case of a weak acid like hydrochloric acid, as you can see demonstrated in this picture right here, if you start off with HF and then you add it to water, there will still be a relatively high concentration of HF. Some of it will dissociate, but only a small fraction, right? So if you could see the particles you'll see basically more HF molecules than H plus and fluoride ions, all right? So that's basically how we can understand the difference between the behavior of strong acids and weak acids. Strong acids will undergo complete dissociation when added to water, while weak acids will undergo partial dissociation, all right? So that's the difference between those two. Okay, so now we're going to look at some quantitative aspects. So the first question here is asking, what is the pH of 2 times 10 to the minus 3 m nitric acid? Now, let me just say this. Whenever you're asked to calculate the pH of any acid, or for that matter, any base, the first thing you have to ask yourself is this acid or base a strong or weak acid? Because that makes a difference, all right? Later on, we're going to see how we calculate the pH of a weak acid. But in this case, we're dealing with nitric acid, which is a strong acid. So how do we calculate the pH of a strong acid like nitric acid? Well, remember we said that strong acids undergo complete dissociation. And that is certainly true in the case of nitric acid, right? So that's the first thing we recognize. And we can write down an equation for the dissociation of nitric acid in water. So when you start off with 2 times 10 to the minus 3 m nitric acid, initially also you'll have no hydronium or nitrate ions present. So that's before any dissociation occurs. So because this undergoes complete dissociation, that means that all the nitric acid will be converted to ions, right? So therefore, at the end of the process of dissociation, you're going to end up with, in the solution, 2 times 10 to the minus 3 m of both hydronium and the nitrate ions. So therefore, in the aqueous solution, we know that we have the nitrate, not the nitrate, the hydronium ion concentration here, which is what we need to calculate the pH, right? So of course, we know the formula for pH. pH is equal to minus log of the hydronium ion concentration. So all you have to do is do the number crunching in your calculator, and it turns out that the pH of the solution is 2.7. And let me remind you that whatever the number of sig figs in the number you find in the log of here, you're going to have the same number of decimal places here. So here we have 1 sig fig, which means that in the answer, you need to have 1 decimal place. All right? So please remember that whenever you find a minus log or the log of any number, whatever the number of sig figs that the log function is operating on, the result will have the same number of decimal places. All right? So please make a note of that. Any questions about this example? Any questions? Any questions?
So like you only log the first product that you get,
I'm sorry?
because you only took log of H3O.
Right, because that's the definition of the pH.
When
P-
NO3.
No, NO3 doesn't come into it when it comes to calculating pH. Right, because the definition of pH is minus log of the hydronium ion concentration. Okay, any other questions? Any other questions? No other questions? Okay, here's another example. Now in this case, they're asking for the pH of a 1.8 times 10 to the minus 2 barium hydroxide solution. So again, as always, you need to ask yourself the question, is this a strong or weak base? And in this case, barium hydroxide is a strong base, undergoes 100% dissociation, and this is the equation for its dissociation. So initially, you're going to start off with 1.8 times 10 to the minus 2 m of barium hydroxide, and before dissociation, you'll have no barium ions or hydroxide ions, right? Now, because of the stoichiometry of the dissociation, you have to take into account that you have, for every 1 mole of this that dissociates, there are 2 moles of the hydroxide ion dissociating. So basically, when all of the barium hydroxide has dissociated, at the end of that process, the concentration of the barium would be 0.018, and the concentration of the hydroxide would be 0.036, which would be 2 times 0.018, all right? So now that we have the concentration of the OH minus after dissociation, how do we find the pH? Well, remember, there's a relationship between pH and a quantity known as pOH. Remember, we talked about that, right? The sum of pH plus pOH is equal to 14.00. So therefore, all we have to do to find the pH is first find the pOH, and then use that equation to find the pH. And this is how we do it. The pH will be equal to 14.00 minus a pOH. the pOH is minus log of the concentration of OH minus, which we determine to be 0.036, and then we do the rest of the calculations. And it turns out that the pH of the solution is 12.6, all right? And another thing I want to suggest, whenever you're doing these calculations, you know, you have to try to think about whether or not the answer makes sense, right? If a solution is acidic, that means the pH must be less than 7. If a solution is basic, that means the pH must be above 7, right? So if you do something like this, and you're trying to find the pH of a basic solution, and you end up with a value less than 7, you know that something is wrong. You did something, you made some error if you're doing, if you're getting that result. So, you know, whenever you're doing these calculations, don't just do it blindly or just follow the process per se. I mean, you have to do that, but also in your mind, you have to think about whether or not the answer actually makes sense in light of what you know about, you know, previous information about acidic and basic solutions and so on. Okay, any questions about, yes, ma'am?
Can you just walk over that?
Which one?
Where we were breaking down the concentrations?
You mean right here?
Yeah.
Oh, okay. So notice this equation here.
Mhm.
For every 1 mole of barium hydroxide here that is being dissociated, you're going to have 2 moles of hydroxide. So basically, if all of the barium hydroxide has reacted, so you start from 0.018 m and you end up with none. That means all of it has reacted. That means that the amount of barium ions produced will be the same, right? Because of the 1-to-1 ratio. And the concentration of the hydroxide will be twice that amount, right? So that's why you end up with 0.036 m at the end of the dissociation process. All right? Okay, any other questions about this? Any other questions? Yes, sir.
Is this chapter gonna be on our first test?
No. 1 and 2 would be the only chapters on test number 1. Okay, any other questions? Any other questions? All right, moving along. So let's talk about something I'm going to introduce to you, something that should be new to you. It's called the acid ionization constant. In some textbooks, they call it the acid dissociation constant, right? And this is a term that is applicable mostly to weak acids. So let's say you have your acid dissociating as shown in this equation, or you can write it that way. Both, you know, will be acceptable. If you want to, well, first, let me just say this. So basically, we have a system in equilibrium. So all the things that we learned earlier in the previous chapter dealing with equilibrium will apply here, including the fact that we can write down an equilibrium expression for this system. So in this case, the equilibrium expression would be products over reactant, if you remember, concentration of, in this case, concentration of H plus times the concentration of A minus divided by the concentration of HA, and that would be equal to a constant. And the equilibrium constant in this particular case is symbolized by Ka here, and Ka is called the acid ionization constant or acid dissociation constant, right? So that's basically what we use specifically for weak acids, right? We don't use this too much in the case of strong acid, because in the case of strong acids, this part here would be 0 because there will be no acid molecules present, which means that Ka for strong acids would be infinity, right? But for weak acids, you'll find that Ka has a certain value, usually very small values, because of course we're dealing with weak acids, all right? So therefore Ka is related to the strength of an acid, right? In fact, we can use the Ka values to compare the strength of weak acids, right? Basically, as Ka increases, as Ka increases, the acid strength increases, right? So if you have 2 weak acids, basically the one with a larger Ka value would be the stronger of the 2 weak acids, all right? So that's one of the utility of Ka values. You can use it to come to conclusions about the relative strengths of weak acids. And this is just a table giving you some weak acids and their Ka values. And what you see is that usually Ka values are very small. The largest one here is hydrofluoric acid. So among weak acids, hydrofluoric acid is a relatively strong acid. And then you see that is 7.1 times 10 to the minus 4. Nitrous acid is 4.5 times 10 to the minus 4. So that is actually even stronger. Acetylsalicylic acid, which is aspirin, has a value of 3.0 times 10 to the minus 4. And then you see the values start decreasing. So you see this one, ascorbic acid, which is vitamin C, has a value of 8.0 times 10 to the minus 5, and then phenol has a value of 1.3 times 10 to the minus 10. So this is typically, excuse me, this is typically what you'll notice for weak acids. They have typically small Ka values, all right? Okay, so we can see if we can learn or apply what we have just learned. So this question is asking, what is the pH of a 0.5 m hydrofluoric acid solution? So again, whenever you're asked to find the pH or the pOH of an acid or base, you need to ask yourself, is this acid a weak acid, right? So hydrofluoric acid, you should all know by now, is a weak acid. So what does that mean? It means that to solve this is not as simple as what we did before. We cannot assume 100% dissociation, right? It is a weak acid and therefore it undergoes partial dissociation. So we have to take a different approach, right? So we have to start off with our equilibrium system. We write down the equation for the equilibrium, for the dissociation of hydrofluoric acid, and we write down the Ka expression for that, and we have to get the Ka value. And by the way, there's a table. Let me show you where it is. And I will provide this table, of course, during your exams or tests or whatever. Let me see if I can bring it up. Okay, so if you go to files, and then go to tables, and then where it says dissociation constant, this gives a more comprehensive list of the weak acids that you will encounter. Weak acids and weak bases and their dissociation constants. And I just want to point, like for example, for acetic acid, it's 1.8 times 10 to the minus 5. You'll notice in the case of arsenic acid, there are 3 Ka values. And the reason why is that arsenic acid has 3 hydrogen ions that it can give up stepwise, right? So for the first dissociation, the Ka value is 5.8 times 10 to the minus 3. For the second dissociation, it's 1.1 times 10 to the minus 7. And for the third dissociation constant, it is 3.2 times 10 to the minus 12. So we normally symbolize the different dissociation constants with Ka1, Ka2, Ka3, right? To indicate the separate dissociation constants. And one pattern that always emerges without any exception is that with each dissociation, the Ka value becomes smaller, right? And the reason for that is that in the case of the first dissociation, you're removing a hydrogen ion from something which is neutral, right? In the second dissociation, you're removing a hydrogen ion from something which has a negative charge. So that is more difficult to occur, and therefore the Ka value would be lower, And then in the case of the third dissociation constant or the third dissociation, you're removing a hydrogen ion from something which has a -2 charge, which is even more difficult, and therefore the Ka3 value would be smaller, right? So that's what you'll observe in the case of arsenic acid here, in the case of boric acid here, in the case of ascorbic acid, which has only 2 Ka values, and so on and so forth. Successive dissociations are usually weaker, and therefore the Ka values would be usually smaller. Okay, and these are Ka values for some weak acids, and then further down we have Ka values for some weak bases, all right? So you'll have access to this table to do the type of calculations we're about to get into in this example. So let me get back to the PowerPoint here. Okay, so as I said before, the first thing you need to do is to write down the equation for the dissociation of the acid, which of course would be an equilibrium situation. And then we write down the Ka values. And of course, you'd have to look up the Ka value for your particular weak acid. This is the equilibrium expression for that. So basically what we're going to do is write down what we call an ice table. We met this before. So basically we're going to write down the initial concentrations for all the species involved. In this case, there's only one species, and that is the hydrofluoric acid, right? And then we're going to put 0 for the H plus and the F minus. And then now we're going to figure out what we're going to put here for the change. Thing is, we don't know what that change is, so we're going to use X to represent the amount of HF that has dissociated. So if X represents that, that means that the change for HF would be minus X. And because of the 1-to-1-to-1 stoichiometry, the concentration, or I should say the change in concentration of H plus and F minus would be plus X and plus X respectively. So therefore, when we write down the equilibrium terms right here, it would simply be the sum of these two lines here. So for the concentration of HF, it's going to be 0.50 minus X. For the concentration of H plus, it's going to be X, and also the same for F minus. And then what we're going to do is plug these terms into this equation, and this is the expression you're going to get, right? The concentration of H plus times the concentration of F minus, that's X times X, so that gives you X squared, divided by the concentration of HF, which is 0.50 minus X, right? And we equate that to 7.1 times 10 to the minus 4. And basically, it comes down to some algebraic steps to solve for X, right? How do we do that? Well, one thing you can do is you can assume that because the acid is weak, right? Because Ka is much less than 1, we can assume that this part here, 0.50 minus X, would be approximately equal to 0.50. In other words, X is so small compared to the 0.5 that 0.5 minus X is approximately 0.5, right? Now that makes life easier in terms of our calculation, because what that means is that the denominator here becomes 0.50x, right? Or I should say 0.50. And then all we have to do is, excuse me, solve for X. And once you do that, right, you're going to get X squared, which would be the product of 0.5 times 3.1, I'm sorry, 7.1 times 10 to the minus 4. That gives you 3.5 times 10 to the minus 4. And then you find the square root of that, and that will give you X. And that X would be equal to the concentration of the H plus right here. So therefore, to find the pH, basically it's minus log of that value. So we put 0.019 here, and you end up with a pH being equal to 1.72. All right. So that's basically how that is done. Any questions? You look puzzled. You all right?
I see.
Oh, I'm sorry. Keep forgetting I'm not transparent.
So,
Mhm.
so because X, we just basically cancel X out.
Right, because we're making an assumption. Now, I'm gonna say more about this later on, but for now, because well, firstly, the acid is weak, right? Which means that if we assume that to be true, which is it is true, then we would expect that the dissociation is weak and only a small fraction of the molecules will be converted to ions. Which means that if X is a change, right? In the case of HF, that X will be very small, very, very small compared to 0.50, such that it's effectively 0, right? So 0.50 minus 0 gives you 0.5. It's an approximation, right? And the approximation makes life easier because you can imagine trying to solve this equation here without that approximation. Basically, it's going to turn out to be a quadratic equation, which we're going to talk about that situation later on.
So
Right?
I could do this with all the acids?
No, that's what I'm about to talk about that. In fact, well, I want to make sure you understand what's happening here before I move on. So any other questions? Any other questions? What about you guys out there in Zoom? Any questions? Any questions out there in Zoom? Going once? Going twice? All right. So, as you alluded to, there may be certain situations where you can't make that approximation, and therefore you do have to go the longer route and solve the equation for X, right? So the question now is, when can I make this assumption or approximation? And the criteria that is used, if you look in pretty much any general chemistry textbook, you'll see that the criteria that is used is that if X is less than 5% of the value from which it is subtracted. So in other words, if the change or the amount of the original acid that has reacted, if it is less than 5% of the original concentration of the acid, then the approximation is valid. If not, then we have to go the longer route, all right? So in this particular case, we take the X value and divide it by the original concentration of the acid times 100%. And when we crunch the numbers, you see that that's 3.8%, which is obviously less than 5%. So in this particular situation, it's okay to make that assumption that we made earlier, right? That X is so small compared to 0.5, that 0.5 minus X gives you 0.5, right? So that's basically what we'd have to do next. After you do what we just did on the previous slide, then you have to check to see if your approximation is valid by determining the percentage. And there's a term for this which you're going to see later on. It's called the percent dissociation. Let me this is equal to the percent dissociation. We're going to talk about this in the next couple of slides. All right. So if the approximation is less than 5%, then okay, we can go ahead with the assumption that we made before. Now, I think this example is a situation where the approximation is not less than 5%. So for example, you go through the same steps and you make your assumption just like before, and you end up with this expression here, and then you solve for X, and it turns out that X is equal to 0.06 M. Then you find the percent dissociation. You divide the 0.006 by the 0.05 times 100%, and you see that this is 12%. 12% is obviously greater than 5%, right? So that means that the approximation is not okay, not valid, and therefore you'd have to go back to the previous earlier parts and solve X using the longer route. And invariably, what this would involve is the solving of a quadratic equation, right? And this brings me to remind you that being the generous person I am, I would allow you to use your calculators, you know, those fancy, what do you call it, TI-83, whatever. I would allow you to use those calculators during test time, right? Because I'm quite sure it would be a bit tedious for you to actually use the quadratic formula trying to solve for X, all right? So I would strongly recommend that you find out how you can program your calculator to do that. Once you do that, all you have to do is enter the A, B, and C values, press execute, and it gives you two values. And we're going to show you how you can tell which value to use, all right? But that's in the next couple of slides, right? Okay, so this is what I was talking about, the percent dissociation, also called percent ionization. It is the concentration of the H plus ions at equilibrium divided by the initial concentration of the acid times 100%. So if you have an acid HA, then the percent ionization would be the concentration of H plus at equilibrium divided by the initial concentration of the weak acid. And what you'll find is that as the solution becomes more and more concentrated, more and more dilute, the percent ionization falls off, all right? So that is what is demonstrated in this particular graph right here. Okay, so I think I have another example lining up, but some statements here concerning how you go about solving these problems. It says, firstly, you identify the major species. Well, I would say even before that, it says solving weak acid ionization problems. Let me just remind you again something I said earlier. If you're asked to calculate the pH of anything, ask yourself the question, is this a strong or weak acid? If it's a strong acid, then you do like what we did before, which was very simple, right? Based on the assumption that the acid undergoes complete dissociation, right? But if you're doing a calculation involving weak acids, then these are the steps that you need to go through. One, you identify the major species that can affect the pH. In most cases, you can ignore the auto-ionization of water because water does undergo dissociation to form H+, but usually that effect is very, very minimal, right? You can also ignore hydroxide ions for the same reason pretty much. So you're going to use the ice table, just like I showed you in the previous examples, to express the equilibrium concentration in terms of a single unknown X. And then you write the Ka expression for the equilibrium concentration and then solve for X by using the approximation method, which I mentioned before. We assume that X is small so that whatever the concentration initially was, when you find the difference between that and X, that's equal to approximately the initial concentration. But if the approximation is not valid, based on the 5% criteria, then you solve for X directly. And then it says, based on that, calculate the concentrations of all species and or the pH of the solution. And of course, this is based on what the question is asking for, all right? So let's look at this example. It says, what is the pH of a 0.122 m monoprotic acid whose Ka value is 5.7 times 10 to the minus 4, all right? So again, you write down your equilibrium equation for the dissociation of the acid, and then you set up your ice table. So initially, you're gonna have 0.12 m of your weak acid, none of the H plus, none of the A minus, all right? That's initially. Again, we're going to say X represents the amount of HA that reacted, so therefore, the change for HA would be minus X, the change for H plus would be plus X, and the same would be true for A minus. Then we write down the equilibrium expression. So for HA, that would be 0.122 minus X, that would be X, that would be X, and then we write down the Ka expression, which is, let me write it over here. Ka is equal to concentration of H plus times concentration of A minus divided by concentration of HA. And then we plug in the terms, these terms here, here, and here into this equation right here. And you're going to end up with this expression right here. And then it's a matter of solving for X. We're going to make the approximation that X is so small that 0.122 minus X is approximately 0.122. That simplifies things a bit here. And then we solve for X, which works out to be 0.0083. Then we determine the percent dissociation. And what do we notice? When we divide 0.0083 by the initial concentration of the acid, we get a value of 6.8%, which is obviously greater than 5. So therefore, it is not an okay approximation. In other words, the assumption that we made will not be valid. So what do? We have to go back to this equation right here and solve for X, right? So the next slide shows you how to do that. It's basically algebra. The result would be a quadratic equation, as you can see here. And this is where your fancy calculators will come into play. You plug in the values for A, B, and C. And what you're going to end up with in this case is, or you can do that if you want to, plug in the numbers into the quadratic formula. But you're going to end up with these two values. One will be positive and the other one will be negative. So the question now becomes, which one do we use? And the answer will be the one that is positive, because remember what X represents. X represents the concentration of the original acid that dissociates. Concentration in real life cannot be negative, right? So therefore, we can therefore exclude the negative value that is given by the calculator and go ahead and work with the other value, which means that in this particular case, X is going to be equal to 0.0081, which would be the concentration of H plus, and then we find the pH, which would be minus log of 0.0081, which would be, in this case, 2.09. Yes, sir.
Can you still do quadratic even if the percentage is less than 5% and still get the right answer?
Yeah.
Like, just to be honest.
Yeah, you could do, you should get the same answer. In fact, what you'll find, because I remember doing this as a student, what you'll find is that the lower the concentration of the acid, the greater will be the difference between the pH calculated with the approximation compared to without, right? So for more dilute solutions, both values will work out to be the same if you do the calculations without or with the approximation. But as the solution becomes more concentrated, then or more dilute, I should say, then the difference between the two becomes larger. Okay. Any other questions about this? Any other questions? Okay, let's move along. So just as we have acid dissociation constants for weak acids, we have also base dissociation constants for weak bases. So one example for weak base is ammonia reacting with water to form ammonium and the hydroxide ion. And that same table I showed you, as I said before, the bottom part of it has the dissociation constant for weak bases. So in the case of ammonia, basically Kb, which is the dissociation constant for weak bases, is given by, again, product over reactant in terms of the concentration. So in this case here, it's concentration of ammonium times concentration of hydroxide divided by concentration of ammonia, and that would give you the Kb value, all right? And just as how there is a direct relationship between Ka and the acid strength, there's also a similar relationship between Kb and the base strength, right? So as the Kb value increases, the strength of the base increases as well, right? And basically, when it comes to solving problems involving weak bases, it's pretty much the same way as in the case of weak acids. The only difference is that very often what you need to do is find the concentration of the hydroxide ions at equilibrium. Whereas in the case of weak acids, your focus would be finding the concentration of the H plus ions at equilibrium conditions. Apart from that, it's pretty much the same sort of steps as we saw in the examples in the previous slides, all right? Again, you have to find the percent dissociation. Again, you have to find out if the percent dissociation is less than 5. If it is less than 5, then whatever approximation made would be okay. But if it is greater than 5, then you have to go the longer route, all right? And again, going back to the same table I showed you. So basically, what we have here, well, this is a different table actually. What we have here is the Kb values for different bases, and we have some Ka values for their conjugate acids. And I just want to point out something, going back to the previous table. Let me go back to this table here, which I could not talk about because I did not introduce to you yet the concept of Kb values. But I'm going to talk about it now as soon as I get there. Okay, this is taking longer than I thought it would. Okay, so going back to this table right here. So remember, this table gives you the list of, a short list of weak acids and their Ka values, all right? Now, if you look over here on the right side of the table, what you have are the conjugate bases of these weak acids. Remember, the conjugate base is what is formed when the acid loses a proton, right? And what you'll notice here is that the Kb values basically increases, right? So this demonstrates basically the relationship between the Ka value for the weak acid and the Kb value for the conjugate base of the weak acid. There's an inverse relationship. As the Ka increases, the Kb, as the Ka decreases, the Kb increases. So basically what we're saying here is that the weaker the conjugate acid, the weaker the acid, the stronger the conjugate base, and vice versa, right? So that's the inverse relationship between the acid and the conjugate base. And same thing is true as far as the relationship between the base and its conjugate acid, which is what the other table demonstrates. As soon as I can get to it right here. This table right here, right? So in this case here, you'll notice that the Kb value decreases, and you'll notice that there's a corresponding increase in the Ka value, right? So you have an inverse relationship between the two. In fact, the next slide we'll be looking at basically establishing the quantitative relationship between the two. So here we have our weak acid dissociating to form H plus and A minus. And the A minus is a conjugate base, so it can act as a base like this. A minus reacts with water to form OH minus and HA, right? So for this equation here, we can write down a Ka expression. And for this equation, we can write down a Kb expression. So if we add these two equations, right, what's going to happen? What will be the net equation? Can anybody tell me? If you add this equation to this equation, what will happen? Or let me ask you this, what will it cancel out? The HAs will cancel out. Okay. And the A minus will cancel out as well, right? So what are we left with? H2O dissociating to form H plus and OH minus. Now you should recognize this equation from what we discussed earlier. What do we call this reaction? It's called the what? It's called the feel free to look in your notes.
The ionization.
The auto-ionization of water, right? This is what happens in all aqueous solutions, not just pure water, right? Now, another question I want to ask you is this. If you add these two equations to get this equation, then what must you do with these values to get the K for this value, for this equation? We learned this in the previous chapter. When you add two equations, right, and you have their respective equilibrium constants, then what would be the relationship between the equilibrium constant of the derived equation in relation to the previous two equations you're adding? When you add two equations to get one equation, to get the final equation, how do you get the equilibrium constant for the final equation based on the equilibrium equations of the equilibrium constants of the two equations you're adding? This was from the previous chapter. How about you guys out there in Zoom? Because these guys here seem to be sleeping. If those guys out there in Zoom are sleeping as well. While you're thinking about it, let me get a record of everybody here. Anderson is here. Is Gonzalez Alba here? Nope. Hickey here?
Yes.
Hickey is here. Hislop? Hislop is here. Jabbar is here. Jones is here. Labrador is here. McKeon is here. Papa is here. Okay, so what's the answer? Adding two equations, you have the respective K, whatever value, Ka, Kb, whatever, Kc. What would be the relationship between those values and the value for the final equation resulting from the addition?
Don't you multiply them?
You multiply them, exactly. So whatever the K value here will be the product of Ka times Kb. And that K value you should recognize as Kw. Remember that? The ionic product of water, right? So basically, the conclusion we can come to is that for any weak acid, the product of Ka for that acid times Kb for the conjugate base of that acid is always going to be equal to Kw, right? That is true for any weak acid. Ka times Kb is equal to Kw. All right, any questions about this? Any questions? Any questions? So basically, what you're going to find in a lot of calculations that you'll be doing in this chapter and the next chapter is that you're going to be using this equation a whole lot, where let's say you can find Kb and you're asked to find Ka, then all you have to do is divide Kw by Kb, or vice versa. If you're given Ka and you're asked to find Kb, then you have to divide Kw by Ka, all right? So that's a very important relationship that you need to keep in mind. So this is again a list of acids and the conjugate bases and their Ka values. So as you can see here, sulfuric acid is a strong acid. So its Ka value is very large. Cannot measure it because it undergoes complete dissociation. And then the conjugate base of that acid would be very small, right? And in each case, if you multiply the Ka for the weak acid by the Kb for the conjugate base of that acid, in each case, you're going to see that the result is Kw which is 1.00 times 10 to the minus 14. All right, so that's the relationship between Ka and Kb. Okay, one last thing I want to talk about, I think, about acids and the relationship between, what time is it? Relationship between the molecular strength and the molecular structure and the acid strength, right? So basically, as we have been learning so far, the strength of an acid is related to the extent to which it undergoes dissociation, right? Now, there are certain trends that have been observed when it comes to looking at the structure of the acid and its strength. And when it comes to binary acids, and we all know what binary acids are. Binary acids are acids which obviously contain hydrogen, but contain one other element, right? So what you'll find is that when it comes to binary acids, the strength of the acid is related to the bond strength, right? And what we're looking at here are all the halo acids of group 7, right? Hydrofluoric, hydrochloric, hydrobromic, hydroiodic. And what you'll find is that as the bond strength decreases, the strength of the acid increases, right? So going down group 7A, you'll find that the acid strength increases for these acids, right? And that is true for group 7A acids, group 6A acids, and others, all right? So basically, the stronger the bond, the weaker the acid, or the weaker the bond, the stronger the acid, right? So that's one trend that is observed when it comes to acid strength, all right? So this is a trend that we will see, right? Hydrofluoric would be the weakest acid, while hydroiodic would be the strongest acid. Now, another aspect of the relationship between the structure of the acid and its strength is when it comes to oxyacids. Now, oxyacids, as you may recall, are acids which contains oxygen. And one of the oxygens, if there's more than one of the oxygens must be bonded to the hydrogen, which will leave in the dissociation. So this is just a generalized structure of an oxyacid. So it will dissociate to form these species here. So basically what we have to look at are the different structural features here that would affect the strength of this bond, right? Now it says here that the OH bond will be more polar and easier to break if, one, if Z, this atom here, which is bonded to oxygen, is very electronegative, or if Z, that same atom, is in a high oxidation state, right? So if this atom is either very electronegative or has a high oxidation state, then the more likely this bond will be broken, and therefore the more likely the acid would be stronger, right? So we have some oxyacids here, like carbonic, nitrous, nitric, phosphorus, and so on. And what we're going to look at in the next slide is basically what is stated right here. So let's look at the first instance where we're looking at the electronegativity of Z. So if you were to compare these two acids, right? This would be bromic acid and this would be chloric acid, right? So the only difference between them, obviously, is that you have a chlorine here where there's a bromine here, right? Now, because chlorine is more electronegative than bromine, what you'll find is that this acid here would be stronger. That bond would be easier to break, right? And therefore, the chloric acid would be a stronger acid compared to the bromic acid, all right? So that is purely due to the fact that chlorine is more electronegative than the bromine, all right? In terms of the other factor, and that is the oxidation number, if you look at these acids here, so what we're doing is comparing hypochlorous to chlorous to chloric to perchloric, right? So you'll notice that the difference between these four acids is that the oxygen content increases, especially when it comes to the oxygens bonded to the chlorine. So in the case of the chlorine here, it has only one oxygen here, which is itself bonded to the hydrogen. In this case here, you have an oxygen bonded to this chlorine. In this case here, you have two oxygen atoms bonded to the chlorine. And in this case here, you have 3 oxygen atoms bonded to the chlorine. And correspondingly, we can calculate the oxidation states. In the case of this chlorine, it's +1, this is +3, this is +5, and this is +7 for the chlorines, right? And what you'll find is that the perchloric acid of all these 4 would be the strongest, followed by the chloric, followed by the chlorous, followed by the hypochlorous acid. So this is basically what you'll observe based on the differences in the oxidation numbers of the chlorine, which is bonded to the oxygen, which is itself bonded to the hydrogen, which will be released upon dissociation, all right? So that's another factor that affects the strength of an acid. Okay, this is quite a lot we have covered. So I think I'm going to stop here, but I want to go to the assignment number 3. Or is it 4? No, number 4, I'm sorry. And let me tell you what questions you should be able to do by now. Okay, so I think we have covered already in class. Okay, did we do? I'm trying to remember. Did we do 4? We did 5? No? But you should be able to do 5. So I'm just going to say 5, 6, 7, 8. Hold on. Oh, that should be 8, not 6. Okay, looks like I messed up with the numbering here, so forgive me. All right, so this one, this number 7 here, you should be able to do all parts of it. This number 8, you should be able to do based on what we have covered so far. Number 9, number 10, hold on, number 10, number 11. Oh, wait a minute. No, you won't be able to do, hold on. Okay, you should only be able to do 11A. So you won't be able to do B, C, E. You should be able to do number 12. You should be able to do number 14, 15. Okay, I would stop there because that one, right, I will stop there. So pretty much all questions up to number 15, but there's parts of number 12 that you won't be able to do. Only, I'm sorry, number 11 that you won't be able to do, excepting the A part. So those are the questions that you should be able to do. The other thing too I want to say here is that by now you should be able to submit your assignment 3 completed. Let me see, did I create a job box for that? No, okay, so let me do that now. So that's assignment 3. And this is file upload. And I'm going to set a due date for this. Well, since you have a test coming up, I'll be nice and say the 15th. Right? Okay, let me make sure it is published. Okay, now it's published. All right, so you should be able to submit that assignment. Remember, please submit it as a PDF document. All right, that makes it a whole lot easier for me to retrieve. Okay, any questions about what we have covered or the test that you'll be doing? The test will consist of, is it 4 questions? I don't have it. I'm upstairs in on my thumb drive. But I think it's 4 questions. Make sure you do all of them. Make sure you bring a pen and your calculator, and I'll provide everything else that you're going to need. And it's based on colligative property, well, solutions and kinetics. You have a question?
So it's like assignment 1 and assignment 2.
Yeah, I would strongly recommend that you review assignments 1 and 2. And like I told somebody last time, I would also recommend that you try to do as many questions from your textbook. There are a lot of end of chapter questions in the textbook for those chapters. So I would strongly recommend that you try those as well. If you have any problems, please feel free See me, I'm up to us today from 3:30 to 7:30, so I'm available if you have any questions. Yes, ma'am.
So are the tests more like workout problems instead of like multiple choice?
Yeah, in fact, I think I have posted as well. Let me see if I can bring it up here. I think I've posted some past exams. Let me see. Past tests. In fact, past test answer keys. This was the final exam I published. Oh, right, okay, so this was 3 tests, 1, 2, and 3. I would strongly recommend that you look at that to get a feel for the type of questions. Okay, finally, somebody in Zoom is asking if we do a Skype account. Oh, yes. 10 points will be added to your first test. Let me remind you. So far, I have 1, 2, 3, 4, 5, 6, 7, 8 students out of 14. So if you have not yet created your Skype account and send me a message or create what is called a contact request and send it to me, please do so. And again, make sure that you include your name and the course number, because somebody last week sent me requests and it was an adult entertainer. So I want to make sure that I'm distinguishing between such persons and you guys. All right. Okay, any other questions? Any other questions? All right, that's it, folks. So I'll see you guys on Wednesday. Yes, sir.
Am I on that list?
Oh,
I think I am, we had, that issue,
let me see. Miss Jones. No, I don't. Hold on. Let's just know.
I Skyped you.
Let me see. Let me see.
I said it's a whole other person, it's not.
Jones.
Oh, here I
Okay,
am.
hold on, let me see here. All right, I don't know how I missed it here. So you are down. Right? No problem. Yes, ma'am.
I asked you to do Canvas saying that I would be available Wednesday and
Oh, okay.
you offered I can take it Friday. Are you still?
I'm gonna be here Friday, from,
It says on here, so we're just up until 7.
yeah, no, hold on. 2 to 6.
Okay, up until 6. Okay.
Yeah, I'll be here Friday, yeah.
Okay,
So you can come by and do it testing.
yeah, I'll try and do it by Friday. And
Yeah.
you said it's just bring a pen and.
Pen, calculator, and I'll bring everything else. The tables, and pens, and a sheet of paper.
What about the formulas?
Well, there are some formulas, and you know something, I've been thinking about that for this test.
Yeah, because.
Because there's,
the first couple chapters, there's just a lot of.
yeah. Yeah, I'll do that too. I'll bring, the formulas I'm thinking about is the rate law, well, the, what do you call it, the integrated rate law equation. So, yeah, I'll bring that. Yes,
Thank you.
no problem.
I can't believe the last name.
Oh, yeah. Yeah, I would have showed you the guy, I would have showed you guys that particular message, but I blocked that person. The first thing I asked her, are you a student of mine? Said something like, no, are you a teacher? I said, okay, I'm not interested. Put her off. Oh. Ah, okay, off to the lab.
Yeah. Not bad. Now I can pull around till. Returning, yes.
So you're going to do the test at 3:30?
No.
Oh, okay.
That's my next class.
Oh,
I'm
okay.
gonna take as much time as I can to study for that.
Yeah, I would recommend that.
Yeah.
Like I said, if you have any questions, please feel free to contact me.
Yeah.